Hello, BC Calculus students. Looks like we're ready for today's notes, and these are definitely monumental notes. These are the last notes of the year, as we are going to finish up with trig substitution, looking at how we evaluate definite integrals. Okay, so first I'm going to show you a couple different situations that will arise. So the first situation is we're talking just definite integrals. So here is a review a little bit of length of curve and also definite integral. One of the things that you probably were wondering, or when, at least maybe you were wondering, is when do these type of situations arise where we need trig substitution? Well, here's a classic example. If you remember when we looked at our length of curves, one of the things we found is that we had to select our functions very carefully if we were going to do them by hand. A lot of times we had to do it with a calculator. Well, now we're going to see with trig substitution, we can do one of these by hand that we couldn't do before. So we're very familiar with our basic parabola, y equals x squared, and we'd like to know what the length of that curve is going from x of -1 to x of 2. So let's see how we're going to do that. So first, remember your formula for length. This is for a function curve defined y in terms of x, not parametrically defined one. So we've got our a to b of the square root of 1 plus our derivative there squared dx. So in this case, what we have to do is we are going to go integrate from -1 to 2 of 1 plus, and notice my derivative of x squared is 2x, so that will be squared there. And so dx like that. So this is our situation that has arisen, and now we're going to have to find a way to integrate this, and our trig substitution will work. So looking at this here, I let u be 2x, which makes my du 2dx, which means that my dx would be 1/2 du. So I can factor that 1/2 out in front and express it like this. Notice what I have done though with my limits of integration. I did change my limits to be the correct limits because I have switched it to the variable u. That means I will not have to switch back to x in the end. I can just leave it as u. At this point here, what you should recognize is this is one of our special formulas. We do not want to try to actually use trig substitution on that. We can, but remember that produces that very long process that I went through where I showed you how to integrate that, but also showed you that it was a real bear, and therefore we usually like to just memorize this as one of our special forms. So memorizing this as one of our special forms, we know it's going to be 1/2 times u times that square root of 1 plus u squared plus, and here's where we have our a squared, so that's our 1 squared there, which is just 1, times the natural log of the absolute value of, and this is going to be u plus our square root of u squared plus 1, and that's all evaluated from -2 to 4. So now going ahead and doing the evaluation process, I did the 1/2 times 1/2 to get the 1/4. And then if I look in here, notice what I get when I put 4 in. I get 4 times, and this would be the square root of 17, plus, putting in 4 in here, I would have the natural log of 4 plus, and that would be the square root of 17, minus, now I have to do it minus, and now I have to put in the -2. So plugging in the -2 here, it looks like I'm going to get -2 times square root of 5 plus, and here I have the natural log of the absolute value. Notice I don't need the absolute values because these are positive, and this will be +2. It's going to be -2, but this is going to be square root of 5. Square root of 5 is bigger than -2, so I've got square root of 5 minus 2. That's still positive like that. Now if I go ahead and distribute the 1/4, get it in a little simpler form, I get this. I mean, it just depends how you want to do this. You don't have to distribute it. I mean, technically I would be there, but probably I would want to clean this up and make that a plus. Other than that, it's probably pretty straightforward to make this a minus, as I've done here. So I put the radical terms in front. So I did the 1/4 times this is just radical 17, distributed the 1/4 to there, and so it becomes 1/2 radical 5 plus. Then I put the natural log terms there, and I get my answer there. That works. Remember, that's an exact answer. You don't need a plus c. There's no plus c to it. That is the actual answer there. And it's not a nice simple answer, but it did give us a chance to do and get an exact answer to this integral without having to necessarily use our calculator. All right, now let's look at another situation that comes up that's not one of our special formulas. So let's look at integrating here, where we want to integrate from 2 to 2 radical 2 of this square root of x squared minus 4 over x dx. Now I'm going to show you a couple different ways to do this. The first way that we're going to do it involves changing our limits of integration when we do our trig substitution. The second way involves not changing our limits of integration and then changing it back to x and then using the existing limits of integration. So let's look at how both those play out. So first off, I recognize this is a trig substitution situation. So build my triangle. At this point, you should be getting pretty familiar with building these triangles and knowing which values to put where. So this is of the u squared minus a squared form. So I set it up like this. And then when I do that, notice first off, solving for the radical, I know that the tangent of theta is my radical over 2. So I know that then my radical becomes 2 times tangent of theta. From this, I need to be able to substitute for x so that I can then get my dx. So my x is going to be, if I look here, I know that the secant of theta is x over 2. So that would just be x equal to 2 secant theta. Taking the derivative, dx would be 2 secant theta tangent theta d theta. Now, normally I would go and substitute right away, but in this case, in order to if I substitute in right away, I would have something in terms of theta, which means I need to have different limits of integration. So I have to change those limits of integration. So what I have to do is I have to get a formula that gives me theta values when I have x values. So I'm going to look at this here, and I'm going to solve it for theta. So solving this for theta, I know that the secant of theta would be x over 2, so theta is the inverse secant of x over 2. So now what I can do is go ahead and get these in terms of theta. So first putting in, when x is 2, if I put 2 in here, I get the inverse secant of 1. Well, that's wondering when the cosine is equal to 1. Well, the cosine is equal to 1 at 0, so I know my theta is going to be 0. Then when x is 2 radical 2, using my upper one, if I put in 2 radical 2 there, I want the secant of theta to be, I'm looking for where the, yes, the secant of theta is radical 2. That means where cosine is 1 over radical 2, or the radical 2 over 2, which is pi over 4. So my theta is pi over 4. So now I can change my limits of integration to 0 and pi over 4. So now I can change everything to theta, and I have my correct limits of integration. So I'll do that here. So here's my resubstituting in with everything in terms of theta. My 0 to pi over 4, I just went and substituted in here. So here is my square root 2 tangent theta. Here is my dx, 2 secant theta tangent theta d theta. And then in the denominator, I've got x, which is 2 secant theta. Notice 2 secant thetas cancel, and all I am left with is 2 tangent squared. So I factored out the 2. So I've got 2 times my integral 0 to pi over 4 of tangent squared theta d theta. This one's not too bad to integrate. You do have to remember your Pythagorean identity, but I can re-express tangent squared in terms of a secant squared, which is nice because that's a known antiderivative there. So I've got 2 times the integral 0 to pi over 4, and tangent squared is equal to secant squared theta minus 1 d theta. This is pretty easy to straightforward integrate, so that's going to be equal to 2 times secant squared is just going to be tangent of theta, and the integral of 1 is just theta, and that's evaluated from 0 to pi over 4. So going ahead, plugging in, when I put pi over 4 into that, I get 1. So I get 2 times 1 minus put pi over 4, I get pi over 4 minus, now I'm going to put parentheses, I'm going to put 0 in, tangent of 0 is 0, minus, and I put 0 in, I get 0. So this is just 0, so this whole thing just goes away. So this is 2 times 1 minus pi over 4, or 2 minus pi over 2. That's one way to do it where we changed our limits of integration. Now let's do it. Let's show you how we would have done it if we had not changed our limits of integration. So what we would have done, going right back to here when we did this, what I would have done is I would have done this substitution here, and I would have left these blank. I wouldn't have put equals between it, saying that this was equal to the original one here, because it's not equal without these limits of integration. But I just would have gone and done that. I would have integrated this, and I would have done all this process, and I would have eventually got to this. But remember, I wouldn't have limits here in terms of theta, so I couldn't put limits there. So I would have got to this 2 tangent theta minus theta, but I wouldn't have had any limits with it. So I just would have had this, the 2 tangent theta minus theta. And now what I would have to do is now, since my limits that I know are still back here in terms of x, I would have to change this back in terms of x. So the tangent of theta, looking back at my triangle, I know the tangent theta is this radical over 2. So I know it's going to be 2 times the radical over 2 minus, and I know theta, once again, we found our theta again, remember, our theta was inverse secant of x over 2. And now that's going to be evaluated from our x limits, because I substituted back in for x. So I never had to change the limits of integration doing this way, but I do have a little bit tougher things to evaluate here. So this goes much as you would expect it to. It's going to be 2 times, putting in 2 radical 2 here. That becomes 4 times 2, or 8. So I get 8 minus 4 for radical 4 over 2, minus. Putting in this in here, I get the inverse secant of radical 2, which we already talked about how that ends up being pi over 4. We'll do that in a second. Minus. And now when I put in 2 here, this numerator becomes 0, so that one's 0. Put 2 in here, I get the inverse secant of 1. We already talked about how that's 0. So what I get is I get 2 times this thing here becomes 1, so that's just 2. And then distribute in here, this thing becomes pi over 4, so I get minus pi over 2. Same answer, either way, but the book talks about doing it one way. And I don't care if you don't have to do all of them both ways, but you should make sure you can do some one way and some the other way, so that you can see both of them, how to do it where you substitute and change your limits of integration, other ways where you just go through and then you change back to x and then put your limits of integration for x in and finish it like that. So that's both ways how to do it. As far as your homework goes, I don't think I've written that down. Your homework is going to be the exercises. And it is going to be 47 through 52. And that's all of them. That's only 6 problems. So pretty straightforward. Hope those go well, and we will have, I've got another Zoom session. I believe actually we don't have another Zoom session before your test. If you need something, talk to me and we can set something up. Obviously we just had a Zoom session, but remember your test is coming up on Friday at 8 o'clock in the evening. So plan on that. They will be AP style questions, but they will not be on the AP Classroom website. I will actually email you a PDF of it, and you will take it while you are logged into Zoom. So, hope to see you. I need to see you all on Friday. So, we'll plan on that. Let me know if there's any issues, and hope this goes well.